Okay, let us see some examples of Z transforms. Okay, let us start with calculating, because we have said in the previous slide that delta of n Z transform is equal to 1. So, let us start with that problem first. Okay, let us see the examples. Example 1. Here x of n is given as delta of n. Now, we have to calculate the x of z for this. Let us do it. Okay. Now, we all know delta of n is what? Delta of n will have a certain characteristic, that is, this is equal to 1 if n is equal to 0 and 0 when n is not equal to 0. So, this is how we define a sequence of delta n. Let us calculate the z transform for this. So, let us say x of z is z transform of x of n, okay, and is given by the formula n is equal to minus infinity to plus infinity, okay, x of n z of minus n. This is the formula which we know. Now, it is existing, we will change the summation terms now. So, what is this now? I can write this as, okay, n is equal to 0 to infinity delta of n z to the power of minus n. So, if we expand this and understand the fact that delta is existing only at n is equal to 0, that means there is only one value. What is that value? Equal to 1, and for all other sequences it is 0. That means, you can write this like this: delta of 0 z to the power of 0 plus delta of 1 z to the power of minus 1, okay, plus delta of 2 z to the power of minus 2, and so on. Okay. So, what all this will equal to? This is only the value which is equal to 1, whereas all other places this is equal to 0. So, this is equal to 1 for all z. Okay. So, this is for all z. So, z transform of delta of n, if you can write it here, z transform of delta of n is equal to 1. Okay. So, this is the answer. What is the ROC? The ROC is the entire z plane. This question first on the board, then we will discuss. We have to calculate the z transform of x of n u of n. Okay. So, this is what let us see the second example. Second example, I want to find out the z transform of a unit step function. So, what are the characteristics of unit step function? The unit step function is, this is equal to 1 when n is greater than or equal to 0 and 0 when n is less than 0. So, this is a unit step function. Let us calculate the z transform for this. So, x of n, x of z, this is equal to z of x of n, okay, and this is given by the summation n is equal to minus infinity to plus infinity, okay, x of n z to the power of minus n. For us, this is a sequence which is existing only for n greater than or equal to 0. So, the summation will be from n is equal to 0 to infinity, and then this is u of n z of minus n. Okay. So, this I can write as n is equal to 0 to infinity 1 z to the power of minus n. So, this I can rewrite this as n is equal to 0 to infinity z to the power of minus 1 n. So, this is equal to 1 by 1 minus z to the power of minus 1. Okay. So, this also I can write this as what? If I take this z to the top, this will become z by z minus 1. Okay, z by z minus 1. Now, what is the ROC? If I want to calculate the ROC, this system converges, this function converges only if z minus 1 is less than 1 or z is greater than 1. So, the ROC is for all the plane that is z is greater than 1. So, let us just write this, summarize here. So, unit step function z transform of a unit step function is equal to 1 by 1 minus z to the power of minus 1, or this is equal to z by z minus 1. So, this is the z transform of a unit step function, and the ROC is existing for z greater than 1. Okay, let us put a mod here. The ROC, we just put a mod here. ROC is for mod z greater than 1. Okay, so this is the region of convergence. Let us see the third example where we have to calculate the z transform of a ramp function. Let us say x of n is r of n, which is nothing but n of u of n. So, this is existing, okay, this is having two values, n for n greater than or equal to 0 and 0 for n less than 0. Now, we have to calculate the z transform for this type of function. So, let us say what is x of z here. X of z for us is z of x of n, okay, and that is given by n is equal to minus infinity to plus infinity x of n z of minus n. So, as you see here, this is existing only greater than 0. So, let us change the summation limits. So, the summation limits will be from n is equal to 0 to infinity, okay, n of z to the power of minus n. Okay. So, if I expand this, I will get like this, that is 0 plus z to the power of minus 1 plus let us say 1 into z to the power of minus 1 plus 2 into z to the power of minus 2 plus 3 into z to the power of minus 3 plus so on. So, this I can write as z to the power of minus 1, I will take common, 1 plus 2 z to the power of minus 1 plus 3 z to the power of minus 2 and so on. So, this will be equal to z to the power of minus 1, 1 minus z to the power of minus 1 whole to the power of minus 2, so expanding the power series. So, that will be equal to z to the power of minus 1 by 1 minus z to the power of minus 1 whole square. So, this is the z transform of a ramp function, which is equal to, again this, if I can write this as z by z minus 1 whole square. Okay. So, this is equal to z by z minus 1 whole square. So, what is the ROC again? The ROC means here z minus 1 must be less than 1 or z must be greater than 1. So, this is the ROC of such a signal. Okay. So, basically what are we doing? We are taking this given signal x of n and are trying to find out whether it is a right handed function or a left handed function. Similarly, we are changing the limits of summation and then we are expanding the power series and we are expanding the power series and finally, we are getting the answer for it. So, a ramp function will have a z transform equal to z to the power of minus 1 by 1 minus z minus 1 whole square, that is equal to z by z minus 1 whole square, and the ROC for such a function is z to the power of minus 1 must be less than 1 or in other words mod z must be greater than 1. So, this is the ROC of a signal which is a ramp function in time domain converted into a z transform which is having an ROC existing for mod z greater than 1. Let us see the fourth example. It is an exponential series that is given. X of n is given as equal to e to the power of minus j omega n u of n. So, what does this unit step function means u of n? That means this is having a value e to the power of minus j omega n for n greater than or equal to 0 and 0 for n less than. So, this is what we know from this given function. So, let us calculate what is the z transform for this. Again the same steps we follow. What is that? X of z we have to calculate, which is equal to z transform of x of n, that is equal to summation n is equal to minus infinity to plus infinity x of n z to the power of minus n. This is the formula which we already know. We are writing it so that we remember it permanently. Okay. So, now let us change the limits. So, these are the limits. So, let us put it here. So, this is equal to n is equal to 0 plus infinity. What is x of n here? E to the power of minus j omega n z to the power of minus n. Okay. So, this I can write as summation n is equal to 0 to infinity, okay, z to the power of minus n e to the power of minus j omega n. Okay, we have just taken n common here. So, what is this value? If I expand this will be 1 plus z to the power of minus 1 e to the power of minus j omega plus z to the power of minus 1 e to the power of minus j omega square plus so on. So, expand this power series, I will get this as equal to 1 by 1 minus z to the power of minus 1 e to the power of minus j omega, or in other words I can write this as z by z minus e to the power of minus j omega. This is the z transform, and what is the ROC for this? The ROC for this must be z must be greater than or equal to 1. This is my ROC. Now, let us start looking at the fifth example, that is calculate x of n of minus n. We have to calculate what is the z transform for this. So, what is x of n given as? X of n is given as u of minus n. That is, this value will be equal to 0 and 1 for n less than or equal to 0 and n greater than 0. So, we have to calculate the z transform this. As you have seen, already we have calculated z transform of u of n, and there we have found that the ROC is greater than 1. Okay, whereas mod z is greater than 1. Let us see what is the ROC for this and what is the z transform for this. So, let us again put x of z for us is the z transform of x of n, that is summation of n is equal to minus infinity to plus infinity x of n z to the power of minus n. Okay, for us, if you see here, for us this is u of minus n z to the power of minus n, okay, and this is minus infinity to 0, as you see here, minus infinity to 0. So, this will be equal to n is equal to minus infinity to 0 z to minus n. Okay. So, now I will change the summation limits. So, if I change summation limits, what happens? So, this will become 0 to infinity and this will become equal to z to the power of n. So, expanding this power series, I will get this is equal to 1 by 1 minus z. Okay, that is what, that is for this series to converge, ROC is mod z must be less than equal to 1. If you see in the earlier problem u of n, we said the ROC is mod z is greater than 1. Now, mod z is less than 1. This is the region of convergence, and what is the z transform of u of minus n? 1 by 1 minus z. Let us see example 6. Example 6 is we have to find the z transform for x of n is equal to a to the power of n for n greater than or equal to 0 and 0 for n less than 0. Okay, so, this is a single sided function. Let us find out the z transform for this. Let us see the solution for this. Okay, now we have to calculate what is x of z. Okay, x of z is given by z transform of x of n, that is equal to summation n is equal to minus infinity to plus infinity x of n z to the power of minus n. This is the formula which we know. Okay. Now, let us substitute what is given to us. It is given like this. As you see here, the function is existing only for n greater than or equal to 0. So, let us write down here. So, x of z will be now equal to summation n is equal to 0 to infinity a to the power of n z to the power of minus n. So, what we will do here is we take n common to bring it to the standard format. So, I can write this as a z minus 1 whole to the power of n. Now, expanding this power series, I will get this as 1 minus a to the power of z minus 1. Okay. So, this I can write as z by z minus a. Okay, taking LCM here, z by z minus a. That means, the function exists only for z greater than a. Okay. As you are aware, This is the ROC of the given signal. Region of convergence is this, whereas the Z transform is for a to the power of n, you have the Z transform equal to Z by Z minus A. Let us see another example 7. Here also x of n is 0 for n greater than or equal to 0 and a to the power of n for n less than 0. So, this is exactly opposite to what we have done. We will try to solve this on similar lines. Let us find out what is the difference between the earlier one and this one in terms of the Z transform and also in terms of the ROC. Okay. So, x of n is given as 0 for n greater than or equal to 0 and a to the power of n for n less than 0. So, this is the slight difference between the earlier problem, this problem. Let us find out what is the ROC for this and what is the Z transform for this type of problems. Okay, let us write down x of z is equal to n is equal to minus infinity to plus infinity x of n z to the power of n. Here, as you see here, the signal is existing from n is equal to minus infinity to 0. Okay. So, x of n for us is a to the power of n and z to the power of minus n. Now, changing the summation sign here, I can write this as n is equal to 0 to infinity a to the power of minus n z to the power of n. So, that is equal to n is equal to 0 to infinity a minus 1 to the power of minus 1 and z. Okay. Expanding this power series again, I will get this as equal to 1 by 1 minus, okay, that I can write as a by a minus z. Okay. So, this is the Z transform of a to the power of n. Okay. What is the ROC for this? The ROC, this will converge for mod z less than a. Earlier, the region of convergence was greater than a. Here, the region of convergence is less than a. So, if you remember the properties of ROC earlier we have given, this is a left-handed side function and this exactly satisfies the property which you have discussed earlier. If you refer to the problem number 6, there also right-handed side ROC we have described certain properties which has been proved correct in that case also. Okay, let us see the 8th problem. It is given as x of n is equal to minus a to the power of n u of minus n minus 1 and 0 elsewhere. So, there is a slight change in the existence of a to the power of n. Let us see how to solve this type of problems. Okay. So, what is given is x to the xn is equal to minus a n. This is for the values u of minus n minus 1. X of n is equal to given as minus a to the power of n u of minus n minus 1. That means, here it is existing from minus infinity to plus 1. Okay. So, let us calculate the Z transform for this. Again, x of z we all know is equal to minus infinity to plus infinity x of n z to the power of minus n. Here for our case, this is existing from n is equal to minus infinity to plus 1, okay, minus a to the power of n. Okay. This is the existence value and this is z to the power of minus n. So, we will just convert this again from my plus 1 to this. So, I can just change the signal summation, I can change the summation from n is equal to 1 to infinity. So, this will become minus a to the power of n and z to the power of n. Now, I cannot apply directly the power series formula. So, what we will do is we will make this summation from 0 to infinity. So, the next step I write here is, okay, we will take out the negative sign here. I will write this is equal to n is 0 plus infinity, okay, a to the power of minus n z to the power of n. Okay. As we are changing the summation from 1 to 0, I have to in fact subtract this extra term that is coming. So, I will write down this here as a z whole to the power of 0. Okay. So, we are not doing any damage here. So, whatever I have added, I am removing it here. So, now that will be equal to 1 minus, okay, we will take that negative sign outside. So, n is equal to 0 to infinity a to the power of 1 z whole to the power of n. So, expanding this, so this I can write as 1 by 1 minus a to the power of minus z. Okay. So, let us take this LCMs and other things. So, let us take the LCM here. So, it will be 1 minus a to the power of minus 1 z minus 1 by 1 minus a to the power of minus z. Okay. So, this will be equal to a to the power of minus 1 z by 1 minus a to the power of minus z negative sign. Okay. So, we can just change this. I can write this as a to the power of minus 1 z by a to the power of minus 1 z minus 1, just taking the negative side outside. So, this is the z transform of the given signal. So, what should be the ROC for this? The ROC for this is, if you see here, a minus z must be greater than 1, that is z must be greater than a, that is the ROC for this. Z greater than a. So, this is the region of convergence. The slight difference between the earlier problems and this problem is, here the summation is not exactly from 0 to infinity, it is neither right handed side nor left handed side. So, we have to readjust this. As we are starting from 1, what we have done during the summation is, we have pushed it to 0, and in fact, we have removed what we have added. So, that we can get this in the standard power series form. Okay, summation. So, that has resulted in this answer. So, this is one of the ways of doing this type of problems. Let us start 9th problem, where x of n is given as a number of series, and then we have to find out what is the z transform for that. So, x of n is equal to 1, 2, 5, 7, 0, 1 with origin at 2. Okay. Let us see this problem. X of n is given as 1, 2, 5, 7, 0 and 1. Here this arrow indicates this is the origin or the starting point. So, if you can plot this, you can just actually plot it here. So, you see here, this is the negative. Okay. So, this point is, let us say this is 1 and this is 2 and then 5, this is 5, okay, and this is 7, there does not exist anything, and this is 1. So, if you see here, how many values are there? This is existing from minus 1, 0, 1, 2, 3, 4. The summation has to be from minus 1 to 4. So, let us see that. So, we have to calculate x of z. So, we have identified what are the different values present in summation. So, now n is equal to, you are starting from minus 1. So, because this is the first point after 0, this is minus 1, and then you can count 1, 0, minus 1, 0, 1, 2, 3, 4. So, this is equal to 4, and then here x of n z to the power of minus n. Let us substitute these values directly. It is a simple problem. So, what I have to do is just take the summation. So, here what is x of n? 1, okay, z to the power of minus 1, that is minus into minus, this becomes plus 1, plus the second term is 2 into z to the power of 0 plus 5 into z to the power of minus 1 plus 7 into z to the power of minus 2 plus 0 into z to the power of minus 3 plus 1 into z to the power of minus 4. So, this is the summation here. So, now you can just sum it up here. So, this is equal to z plus 2 plus 5 z minus 1 plus 7 z minus 2 plus z minus 4. So, this is my x of z for these cases. So, this is a summation which is happening. So, the ROC will be the entire z plane except z is equal to 0 and infinity. So, that is the values where this will not converge, otherwise the z transform will be for the entire z plane. This is one problem. So, here the significance is this we have taken here. So, this is 0. So, we have to count the number of sequences, how many are there. So, you can just, we have counted, we have got 4 here, then we have just substituted these values, these are the amplitudes. So, we have put it here, so we got the z transform this. We will look at a similar problem here, another problem but with a slight difference. So, this will completely cover these type of problems which are asked in any of the competitive exams. Let us see another example, that is 10th example. Here x of n is equal to 1, 2, 5, 7, 0 and 1. As there is no arrow mentioned in this type of sequences, the first one is the starting point, that is at the origin. So, let us look at this problem. So, x of n is equal to 1, 2, 5, 7, 0, 1. There is no mention of an arrow, that means this is our starting point or the origin point. Let us see how many summation terms we need actually. So this is 0, 1, 2, 3, 4, 5. So there are 5. So summation has to be 5. So let us put that here. So what is x of z here? X of z is equal to summation. Okay. What is it we are starting from? N is equal to 0. Perfect. Okay. How many terms are there? 0, 1, 2, 3, 4, 5. X of n z to the power of minus n. So let us start this. So the first is 0, so that is 1 into z to the power of 0 plus 2 z to the power of minus 1 plus 5 z to the power of minus 2 plus 7 z to the power of minus 3 plus 0 z to the power of minus 4 plus 1 z to the power of minus 5. So I will get it like this: 1 plus 2 z minus 5 z minus 2 plus 7 z minus 3 plus z minus 5. This is my x of z. Okay. So this is the x of z for a series of points given here. So this we will get the x of z like this, that consists of 1 plus 2z minus 1 actually. So let me repeat this here. I will again do this here. So x of z is equal to 1 plus 2z minus 1 plus 5z minus 2 plus 7z minus 3 and z minus 5. So earlier recording, please rewrite this because I have read it wrong. So just copied it here. X of z is equal to 1 plus 2z minus 1 plus 5z minus 2 plus 7z minus 3 plus z to the power of minus 5. This is our x of z. Let us do the next problem. Is x of n is equal to 2 to the power of n for n less than 0 and 0 for n greater than 0. X of n is given as equal to 2 to the power of n for n less than 0 and 0 for n greater than 0. So these are the values given. So as you are aware, this is again a left-handed side function, so we have to calculate that. So what is x of z for us? X of z is z transform of x of n, that is given by summation n is equal to minus infinity to plus infinity x of n z to the power of minus n. So let us substitute these values here. As you are aware, the x of z here is equal to x of n is how much? And as you see here, this is existing from minus infinity to 0. Okay, and then you have 2 to the power of n z to the power of minus n. So let us just take this, transform the summations here. So this will become n is equal to 0 to infinity 2 to the power of minus n z to the power of n. So this I can write as n is equal to 0 infinity 2 to the power of minus 1 z whole to the power of n. So now what is x of z here? That will be equal to 1 by 1 minus 2 to the power of minus 1 z. So I can just take this 1 by 1 minus z by 2. So this will be equal to 2 minus z. So this is my z transform for this 2 by z 2 minus z. So this is the z transform of this, and what is ROC? Because this should not converge, so z must be less than 2. So here ROC is z must be less than 2. So we will get the ROC here, and this is the z transform for such a signal. Let us see the 12th question. 12th question is x of n is equal to a to the power of n existing from for values 0 to n capital N minus 1, a is greater than 0 and 0 otherwise. Let us see this problem. So let me put it down on the board. X of n is equal to a to the power of n, and this is existing for n. Okay, this is the values into which this is existing. Also given is a is greater than 1 and 0 elsewhere. Okay, I will read this again. X of n is equal to a to the power of n existing between 0 to n minus 1, a to the power of where a is greater than 1 and its value is 0 elsewhere. So let us see how to solve this problem. Okay, there seems to be a slight difference in the limits where this is existing, but let us put it down as it is first of all, then we will try to see how we can solve this type of problems. So let us see this here. X of z can be written as, again I am not writing everything, but definitely we will write this formula because this is what we have to remember always. So, let us put it that here, and for us let us put what is given to us. So, what is given to us is n is 0, perfect, and this is existing only up to n minus 1, that is what we have put it here. This, what is this value? This is a to the power of n, z to the power of minus n. Okay. So, let us see how to solve these types of problems. Okay. So, this is n is equal to 0 to n minus 1, a to the power of n, z to the power of minus n. So, because of the summation limits a little different, we have to take into consideration of earlier knowledge, where we will put it here what the formula which we know. Okay. So, we know this, we are using it here. Let us say this is what we have, n minus 1 x to the power of n. So, this summation, this is equal to 1 minus x to the power of n by 1 minus x. So, this is the formula which I have to apply here. So, this I can write this as actually n is equal to 0 to n minus 1 a z1 minus n. So, we will take it like this. So, this is x for us, in our case this is x. So, using this I can write x of z here as, okay. So, what can I write here, x of z? This is my x. So, I will use this formula. So, that will be equal to 1 minus a z minus 1 whole to the power of n divided by 1 minus a to the power of z, a to the power of z minus 1. So, this is the answer for such type of questions. So, here the significance of this question is we should know this formula. Once this formula is known, it is actually very easy to calculate the z transform of this. So, that is what we have written here. So, for us x is nothing but a z to the power of minus 1. So, we brought it to that notation, and then we have put what is the z transform of such a signal. Let us see the next question, that is 13th question. This question is based on linearity or superposition property of the z transforms. So, the example is, I read, x of n is equal to half to the power of n u of n plus 1/3 to the power of n u of n. So, we have to solve this problem. Let us put it here on the board. X of n is equal to half n u to the power of n plus 1/3 n u to the power of n. Okay. So, this I can write as x of n is equal to x1 of n plus x2 of n. Okay. So, if this is having a z transform of x1 of z, and this is having a z transform of x2 of z, then all this get added, I will get the total x of z. So, what we do here is, because of this superposition property, first of all I will find out what is the z transform of this, then I will find out what is the z transform of this. We add these two together, then we will get the total z transform of a given signal. So, let us take first x1 of n, assume that this is having a z transform of x1 of z. So, x1 of z is equal to summation, okay, this is u of n. So, it is existing from 0 to infinity. So, this is n is equal to 0 to infinity half to the power of n z to the power of minus n. So, I can write this as summation n is equal to 0 to infinity z to the power of minus 1 to the power of n. So, this is what we could write. Now, what is this? When I expand this, I will get this answer like this, 1 by 1 minus z minus 1 by 2. So, this I can write as 2z by 2z minus 1. So, what is this ROC for this? Let us call it ROC as 1. So, here R1 we call this ROC, and z must be greater than or equal to half. So, this is the ROC for the first case, that is the first part x1 we have calculated. And now, let us calculate the x2 part of it. Okay, what I will do is, we will make a small note here somewhere. The x1 of z is here 2z by 2z minus 1 okay, and this is having an ROC which we call it as z is equal greater than half here. Okay, now let us calculate the x2 of this. So x2 of z is equal to summation n is equal to 0 to plus infinity 1 by 3 whole to the power of n z to the power of minus n. So again expanding this, I can write this as n is equal to 0 to infinity. So z to the power of minus 1 by 3 n. So I can write this as 1 by 1 minus z minus 1 by 3, that is nothing but 1 by 3z. So I can write this as 3z by 3z minus 1. And the ROC for this, we call it as R2, that is equal to z is greater than 1/3. Z greater than 1/3. So this is the ROC for this. Now to get x of z, I should add this and this, so that I will get a x of z which is a combination of this. That is what superposition theorem says. So what the superposition linearity theorem says? If x1 of n is having a z transform x1 of z and x2 of n is having a z transform of x2 of z, we calculate these two separately and add them to get a total z transform. That is what we have done here. Now what does ROC speak of? The total ROC will be the intersection of these two ROCs. So intersection of these two ROCs will be the resulting ROC for such a signal. Let us see this. Okay, now let us put x of z. X of z is equal to x1 of z plus x2 of z. So that is equal to x1 of z, we already know, 2z by 2z minus 1 plus 3z by 3z minus 1. Actually, you can simplify this. Let us take the simplification. Okay, let us simplify this. This will be equal to 2z into 3z minus 1 plus 3z into 2z minus 1 by 2z minus 1 into 3z minus 1. You can simplify this to get a further answer. So now we have to look at the total R. What is the total R? That is the total ROC will be equal to R1 and R2. Okay. So I mean we can just draw it here. How does that ROC look? Okay, let us take this as a unit circle. Okay, so this is your unit circle. This is 1. Okay, this is 1. Now the ROC is half here. So this is half. So ROC will be beyond this. Okay, so this will beyond this will be our ROC. In the first case, this is in the case of a R1. So when I talk about the second case, this will be somewhere here because this is 1 by 3. Okay, when I say intersection of these two, this will be beyond this. So the ROC of these two will be z greater than half. Okay, so that is the intersection, because this is greater than 1/3 and this is greater than half. So from 1/3 to half there is no intersection. After half only there is an intersection. So that is why the ROC for such a signal will be greater than half. Let us see the 14th problem. X of n is equal to alpha to the power of n u of n plus alpha to the power of minus n u of minus n minus 1. Let us solve this problem again on similar lines. Okay, x of n is equal to alpha to the power of n u of n plus alpha to the power of minus n u of minus n minus 1. So let us take this again. Let us classify this as x1 of n and let us call this as x2 of n. So let us calculate this z transform separately and then sum them up. Okay, let us start with the first one and let us say this is having an x of z as the x1 of z as its Fourier transform and this is having x2 of z as its Fourier transform. Okay, let us calculate x1 of z. So that is equal to summation n is equal to minus infinity plus infinity x of n z of minus n. Okay, z to the power of minus n. So this I can write as, this is u of n. So n is equal to 0 to infinity alpha to the power of n z to the power of minus n. So, this we can put it like this. So, this will be equal to n is equal to 0 to infinity alpha z to the power of minus 1 whole to the power of n. Now, x1 of z will be equal to 1 by 1 minus alpha z to the power of minus 1. So, this I can write as z by z minus alpha. Okay. So, what is ROC? ROC will be z greater than alpha. So, here two cases can be considered. I can consider the value of alpha as greater than 1 and alpha as less than 1. So, this is the case 1 where we will take alpha is greater than 1. So, let us call this as case 1 where alpha is greater than 1. Okay. So, this is my Z transform for this. Similarly, let us calculate the Z transform for the second part. Okay, let us take x2 of Z. As you see here, this is existing from n is equal to minus infinity to 1 alpha to the power of minus 1 z to the power of minus n. Summation n is equal to minus infinity to 1 alpha minus n alpha to the power of minus n and z to the power of minus n. Okay. Let us look at this problem. Okay, I am just checking it's minus n or not. Let us, I will repeat again this. X2 of z is equal to minus n to plus 1 alpha to the power of minus n z to the power of minus 1. Let us change the signs of the summation. So, how do I do it? Okay, so what I will do is, as we have done earlier, this is a famous problem. So, I am shifting them. So, when I shift, this will become plus and this will become plus. Okay, that is what we have. So, again the problem is we have a summation starting from 1. So, let us make the summation start from 0 and subtract it. So, what I will do here is I will add 0 term here and then subtract there. So, this will be alpha z n minus alpha to the power of 0 z to the power of 0. So, this will be equal to 1 by 1 minus alpha z minus 1. So, that will be equal to 1 minus 1 plus alpha z by 1 minus alpha z. So, this will be equal to alpha z by 1 minus alpha z, or I can just write this as z by 1 by alpha minus z. So, here ROC will be z greater than 1 by alpha. So, earlier case ROC was alpha, z greater than alpha, and here ROC is z greater than 1 by alpha. Now, you can add these two terms what we have got earlier, so that you can get x of z. So, x of z is, you can just add them, okay, simple addition. So, you will get this, and total ROC will be R1 intersecting with R2. As you see here, for the case 1 alpha is greater than 0. So, you have an ROC, one ROC R1 is greater than alpha and another ROC is 1 by greater than 1 by alpha. So, there is no intersection between these two. So, Z transform does not exist because there is no region of convergence that is existing. So, x2 of z is 1 by 1 minus alpha z minus 1. So, we taken the LCM here and then we got alpha z by 1 minus alpha z. So, this is z by 1 by minus alpha minus alpha. So, here the region of convergence for this is, okay, z must be less than 1 by alpha. Okay. So, that is greater than alpha and this is less than 1 by alpha. So, the total region of convergence will be R is equal to R1 R2. So, there is no convergence between these two signals. So, there is no intersection points available for R1 and R2. So, Z transform does not exist for this question. If I look at the case 2 here, case 2 I can take alpha less than 1. When I take this, there is an intersection point. So, Z will have, so this is the ROC in a second case. So, Z transform exists where alpha is less than 1. Okay, let us summarize today's session of Z transforms. As we have seen in this session, we have found out where Z transform is used. As you are aware, Laplace transforms and Fourier transforms used in cases where continuous time signals are there. So, whenever discrete signals are there, we go for a Z transform. And also, one of the main advantages of using a Z transform is when I have a difference equations, they will be converted into simple algebraic linear equations when I apply a Z transform to this. Also, we have seen that a system having h of z as system functionality, then it is easy to find out the system's response. So, h of z is known for a system when the output y of z will be the product of h of z and the input x of z. So, when I apply delta signals, delta of n to the input, then x of z will be 1, as you have seen in one of the problems. The first problem in fact we have solved, we have found out that delta of n is having a z transform 1. In that particular case, y of z, that is output, will be equal to the system's function, that is h of z. Then later we have seen difference properties of z transforms. Then we have found out what is ROC, that is region of convergence for which z transform exists. Then we have found out different properties of ROC under which exists, and we have proven those ROC's properties in our examples, various examples which we have seen. And in fact, in one of our problems we have used the superposition theorem also to solve this.